5, 4, 3, 2, 1. Why do we have... Okay, we're just going for it. There we go. That's better. That's not good. Oh my goodness. Welcome to Retraice, segment number 70 for Sunday, December 4th, 2022. It's 11 p.m. Eastern, 8 p.m. Pacific. I got a little error message from Google when I went live. And anyway, Retraice about what's going on out there. Today we're going to talk about partial derivatives and gradients. Don't be scared by that. Trust me, we're not going to do anything crazy. It's not going to be boring. It's going to be action-packed. You already saw the mountain. I already spoiled my thunder. You saw the mountain, if you were paying close attention. Retrace about what's going on out there. The short answer to that question is computer control. The long answer is natural, artificial, and strategic intelligence and humanity, which is the best part. Retrace is for outsiders, but we came to the conclusion that outsiders are not players, and the computer control game is player-oriented, so now we're learning to play. What does learning to play mean? It kind of maybe means becoming autodidactic artificial intelligence engineers? Maybe. We'll see. Nobody knows for sure. Okay. Getting that error message again. We got to go. This is what we're doing. What is a gradient? No, wrong question. Okay, so where are we at? We're in the Math and Code December to Remember event to ramp up our study of AIMA4e, Artificial Intelligence, a Modern Approach, Russell and Norvig, 4th edition. We're going to do that January to June inclusive, 6 months, but we're front-loading the Math and Code in December to make sure that there's nothing that's really going to trip us up or bog us down or do any sort of tar pity sort of thing to us in those sweet 6 months to come in 2023. So what does that look like? Well, first we went to page 48. That was the first place that real pseudocode occurred in the book and serious mathematics of any sort, summation, notation, a couple of things that required some thinking. We did what we were going to do with that. We came up with a little, can I remember, ECMP, English Code Math Progress. Yeah, came up with a little strategy, a little loop for dealing with the technical. Check out Retrace Notes segment for Re69 if you want to see the gist of that, or go check out the whole segment. And now we're moving on. Look, the book is 1,000 pages. We're not going to exhaust the mathematics and the code, but we want to make sure that we're ready for the stuff, the challenges, the stuff that the tar pits. We want to go deal with the tar. We want anti-tar, whatever that means. I think the next page is really is 120. Well, it starts a little bit on 119. I mean, the section starts. There's some pseudocode on 119, but that's not the stuff I'm interested in. Page 120, we start talking about. Okay, so here's the problem they describe. Here's the toy problem that they describe. You've got Romania. It's Romania, right? Is it Romania? Yeah, Romania. You got Romania, and you got a bunch of cities in Romania. Let's say that there are 10 or maybe a dozen. And you're going to place 3 different airports on the map of Romania, and you want to place them such that basically everybody is the ideal distance from at least from their nearest airport. So if you were just going to place one airport, you'd sort of it's going to be somewhere in the middle. You'd measure all the distances, and then you would try and optimize the location of that airport so that in a simple way, so that the sum of all the distances is as small as possible. I think that's how you would do. That's how you would place a single airport. But you can't do that with 3 airports because moving them around affects the other ones. You can move an airport a little bit further away, and suddenly the city that was sort of close to that airport is now closer to another airport. So you're moving 3 pins on the map, and the problem that we want to solve in our artificial intelligence situation, our AI engineering challenge, is to locate those pins, and the way that you do that is something called gradient descent. Is a method called gradient descent, and gradient descent looks like doesn't look like a mountain. I keep doing that wrong. It looks like maybe just that is sort of what a gradient looks like in mathematics. It's this the symbol that represents a gradient of a function is this little upside down delta. So if you've got a function, I didn't put the function the function equation that they give in the book, but it's a function of. It's okay. Let's just stop for a second here. This is hard to talk about at a basic level. So this is vector calculus. So you're combining calculus, which is the mathematics of continuous lines and spaces, and the mathematics of change, the mathematics of however you want to think about calculus. It came about mostly because of physics, but it's applicable to every part of the world that's not discrete, which is the whole world. And then there's linear algebra and vectors and matrices, and that's a very sort of system of equations. Okay, they all have the same variables. Let's just manipulate the coefficients, the multipliers of the variables in each variable's term, and solve for, find solutions that satisfy the equations, systems of equations in multiple variables. I know that stuff. If you're not a math person, I know that stuff's not gonna help much. But anyway, you put those two things together, calculus and linear algebra, or at least vectors, and you get vector calculus. And gradient descent is okay. Let's go to the mountain. Go to the mountain. Okay. There. So let's say you're in this place, this green field, and you want to get to the highest point. Okay? But you're blind. You're in this field of hills. Hillocks? Is it a hillock? And you want to get to the top of that one in the distance. That obviously, although it's not clear if the one front and center is higher than the one far off to the left, probably the one far off to the left. But anyway, you're blind. How do you get to the top of that mountain? And I should say, let's just remind ourselves. I am your podcaster. I should not be your mathematician. I should not be your math teacher. I should not be your artificial intelligence teacher. I'm going to say some things. I do it. I sometimes like sequence and series. I keep saying the wrong word with that. I did it with another one too. Equation and expression. I sometimes call an expression an equation. It's just because I'm not used to talking about math. I love math, but math doesn't love me, and math people don't love me, and so I don't get to talk to anybody about math, so I'm not really good at catching myself when I use the wrong words. That, and the fact that I'm not good at it at all, but I just love it, so I know, more than the average person. But anyway, don't take this stuff to the bank. The bank should have nothing to do with what I'm going to tell you today, okay? So if you're blind and you want to get to the top of that hill, you need some way of doing it. And one way of doing it involves feeling how steep each little part of each little hill is. There are problems with just feeling the steepness of wherever you're at and always trying to go up, because you'll reach what's called a local maxima. You'll get to the top of one hill and you won't know that there are other hills that are higher, and if your method is only to go uphill, then you'll basically arrive at the nearest local maxima, the top of the nearest hill to wherever you start. Okay. So it's like a landscape. What does this have to do with airports in Romania? Well, you can represent a lot of problems, optimization problems. We're optimizing something. We're trying to optimize the location of airports. We're trying to optimize our elevation in the case of the hillock, I think is what you would call that. There's a lot that goes into this. There's a lot of sort of AI algorithm thinking that you have to put into it. And then the mathematics is separate to that. And we're not going to, knock all that over in one pass here. I'm torn between how hard I should try to figure out how to explain all this, and depth versus breadth, depth first search versus breadth first search. So I can either in this December to remember, and this is my inclination, is to go hard at the mathematics of this. I can already feel like if I keep going with this, okay, and I do what I thought I was going to do, I'm going to show you the equation for the operator, the gradient operator on the function f, and the function is of a vector, so a vector of 3, in this case, of 6, a 6-dimensional vector space. And then I could sort of throw some things at you to help you understand, but I'm not there yet. And it's been one day, and I tell you, man, I was up really late last night because of math, basically. But actually not fun math, not like, learning new things, but like font. The font of that equation right there. Why does it matter? It's because in mathematics, there can be very subtle differences between notation and symbols. And if you don't get exactly the right, you can, if you're not sure that you're dealing with, in this case, the partial delta there. Anyway, okay. Can you tell I've been up late? So it comes down to this. On page 120, this is in the searching section of the book. Remember, we had the 6th section, or not, it's in the solving problems by searching. This is searching complex environments. This is a continuous environment. It's not like there aren't stairs up and down the hills of the places you want to go. Oh, okay. I don't want to try and do something I can't do. I've said from the beginning that we're not trying to teach artificial intelligence. There might be some learning that happens accidentally, but I don't want to try and do something I can't do yet. And so I have to make some decisions about how hard to go with this, because I really want to. I really want to go hard at the math. There's some really cool things that we can do if we focus on this particular. And this is the stuff too that, like there isn't a lot after that. If we can handle the vector calculus on 120 and surrounds, what the probability is going to get us? No, there's nothing else. It's just like partial differential. We might have some, a little bit more calculus, but it's like if I can plant a firm footing for us, but it's going to take a bit of time because I've got to tighten up my explanatory understanding, my active knowledge. You got the passive knowledge. You look at something. I look at an operator like a I don't know, like a gradient operator or a partial derivative, and I kind of know what that's about. I kind of know that like a partial derivative is like, okay, you got a function of 2 or more variables, so it's sort of like a hill or it's some sort of 3-dimensional shape. I just showed you one, right? And if you slice any one of those shapes along, an x-axis or a y-axis, or you wouldn't do it. Usually x and y are on the I guess everybody does it differently, but the z goes up when you're doing stuff like this. It's different in different contexts, but so you wouldn't slice the horizontal. You would slice vertically, either perpendicular to the one direction or another. And if you do that, and what you're doing is you're holding one of the independent variables, either x or y. You're holding it still, basically. And if you differentiate when you do that, then you're calculating a partial derivative, which is a rate of, it's a function that's a rate of the change of the function, of the original function. And that's calculus, and that's that requires some explanation. Like I'm not going to be able to land that plane right now. And then when you look at the equation here, what we have is a partial derivative of the function f with respect to x1, partial derivative of the function f with respect to y1, and then with respect to x2 and y2 and x3 and y3. This is a 6-dimensional space, so you can't visualize it. You're usually only dealing with 3 dimensions, certainly in physics, or maybe 4 if you had time. but this is AI programming. We're going to do a lot of n-dimensional work with vectors, and so anyway, okay. I'm going to leave it there because I don't want to waste your time. Okay, let me get back to you on what we should do next. And so our methodology, or our method derived from our methodology is you start with English. I feel like I've done a little bit of English for you here, but I'm not there yet. I'm not there. I can't explain it cleanly. Then we're into the code. They don't actually provide any pseudocode to do with any of the gradient descent problems that they discuss in the whole book. There's no gradient descent algorithms. But that's because this stuff is, you're going to be using tools. You're going to be using tools that are already developed. You're not going to be writing your own code to find partial derivatives and gradients and all that stuff. You're going to be using libraries. So we would go into the code. So we have that. Like there's code. It's not in here, but I have it in other books that we can get serious about the math. And the better we are at the math, the easier everything else is going to be. And we go from code to mathematics. So we're mixing the code and the mathematics together in what I just said. And the mathematics would tell us the limits of what we can do. And then finally, we want to go do something useful. If we can use the code, if we can use the tools out there that can do things like gradient descent and vector calculus problems in general, without failing to understand what we're doing, we're gonna be in a good position. We're gonna be well on our way. But I've only got a month to do this. Not even now. It's the 4th, and I don't know. I got decisions to make. Let's leave it there. All references. There will be no references. Will be in the PDF notes. Some references. Did I have any amendments or corrections? Just the thing I said a couple of times: sequence when I meant series and vice versa. And then expression when I meant equation. Sorry, it's a bad habit. That's it. This is Retraice segment number 70. I'm so disappointed. Like I really thought I was going to be able to go on this, but this is hard. This is like to bring that down to earth. Maybe tomorrow. Maybe tomorrow. All right. This is segment number 70. Same time tomorrow, 11 p.m. I'm tired because I was up late working on this stuff. All right. We'll do the same time tomorrow, 11 p.m. That'll be Retraice segment number 71 for December 5th. Today's December 4th. 8 p.m. Pacific, 11 p.m. Eastern. Signing off.